And I will begin to let folks in. Good morning, everyone. Thank you for joining. We'll take another minute or so to allow more people to join. Good morning, everyone. Thank you again for joining. I think we can go ahead and get started. And I'll continue to let people in from the waiting room. Thank you all for being here for the next installment of the TUMI EBus mission webinar series. Today, we are joined by the ICCT to present the new fleet operations monitoring tool as part of the technical assistance offering we give to our cities through the coalition. Next slide, please. We do have interpretation available today in Spanish, Portuguese, and English. You can look for the interpretation icon at the bottom of your Zoom screen and let us know in the chat if you have any difficulties finding that, and we can help you. Next slide. This presentation is done in collaboration with the Transformative Urban Mobility Initiative, or TUMI EBus mission, on behalf of the Federal Ministry for Economic Cooperation and Development, and implemented by GIZ. World Resources Institute is a proud coalition member, along with the ICCT, and everyone you see listed here. I'm joined today by Hussein Basma, an associate researcher at the International Council on Clean Transportation. I'll begin by giving a brief introduction of the TUMI EBus mission and come back later to monitor the Q&A. So any questions you have, please do drop them into the chat at any point. And again, my name is Lidia Henderson. I'm an associate on the World Resources Institute Global Electric Mobility team. Again, a quick agenda. I think we can skip to the next slide, please. And the next one. So like I mentioned before, the coalition of 7 global partners are working together as a coalition on the TUMI EBus mission to dramatically advance the adoption of electric buses in major cities in the global south. The program works closely with 20 targeted deep dive cities and is hopeful to scale massively to at least 500 additional cities, beginning with 100 cities in this project year, to continue our large-scale change. Next slide, please. These are the deep dive cities that we work in, and the global and local partnership that the TUMI EBus Mission Coalition provides offers direct technical assistance to participating cities to help overcome barriers to EBus adoption. And if you go to the next slide, Mende, we can show the network of city network cities that is part of our scaling effort to go from 20 deep dive cities to hundreds more. The city network is facilitated by our partners ICLE and UITP, which is a network of peer-to-peer learning with other city network cities, as well as between the city network and deep dive cities, where members benefit from shared knowledge and resources to aid the transition to electric bus fleets, including trainings such as this. And if anyone has questions or would like more information on becoming involved with the EBus mission or our coalition in general, please do let us know in the chat or follow up with us afterwards. Next slide, please. I think we can go ahead and just allow Hussein to give his presentation on this tool. Again, we'll be monitoring the Q&A. And Hussein, if you want to take over with your slides.
Thank you very much, Lidia. Let me share my screen. Okay. Okay, can you see my slides in full screen mode?
Yes.
Super. Yeah. So yeah, thanks again, Lydia. This is Hussein from the ICCT. I'm a researcher at ICCT, and I work for the heavy duty vehicles team. My main areas of expertise cover the techno-economics of zero emission trucks and buses, namely battery, electric, and hydrogen trucks and buses. And today we'll be talking about the TUMI EBus tool, which is a tool that we have been working on. We've been developing internally at ICCT as part of our Fleets Center in collaboration with my colleagues, Carlos Bueno and Oscar Delgado. And yeah, let's just kick off this presentation then. Okay, I guess it's working now. So first of all, why are we interested in developing such tool, or what are the goals of trying to have such a platform? Well, we are all aware, I guess, of the environmental performance of electric buses. So electric buses as a technology, they do have a superior environmental performance when we compare them, for example, to diesel buses, to hybrid buses, or even to hydrogen buses. And this is mainly due to their high system energy efficiency. So we have a very efficient energy conversion inside electric buses, unlike the inefficient internal combustion engines or fuel cells that actually face lots of losses, which reduces their efficiency. In addition to that, electric buses, they have no pollutant emissions in their tailpipes, simply because there is no combustion of any fuel or any carburant in this case. On top of that, electric buses, they have the potential to provide some significant greenhouse gas emission reduction, depending on the carbon intensity of local electricity grids. But in general, yes, they can provide some significant reduction in the greenhouse gas emissions if we compare them to diesel or also to other technologies. So just to say that electric buses, they do have an excellent environmental performance under the right conditions, but nonetheless, this technology is still facing some challenges that are holding off or holding back the massive or the wide-scale deployment of electric buses, at least outside China. We know that in China, like almost 90 or 92% of the EBus fleet in the world are located in China. And more recently, we started to see some cities in Latin America, like in Bogota or in Santiago de Chile, where we have lots of new electric buses. And these two cities are actually becoming the biggest hubs for electric buses outside China. Nonetheless, the wide deployment of electric buses is still really not at the pace that we would like to see, given the technology, environmental performance, and high system energy efficiency. And why is that? It's all about these challenges facing electric buses. And I am categorizing these challenges under three main umbrellas, as you can see in this slide. So we have some technology related challenges. And when we talk about technical challenges, we're mainly referring to the challenges related to the design of the batteries or the battery sizing approaches, and also the charging infrastructure. So how many chargers do we need, where to locate these chargers, what type of charging technology we need, and many other questions related to the technology viability or technical feasibility of these new electric buses. Another umbrella of challenges, I would say, is the economics of electric buses. So we are talking about a pretty new technology, and this technology does have a very high investment cost, simply because we are using some very expensive material for batteries, which significantly increases the cost or the investment cost of electric buses. The last, but definitely not least, set of challenges facing e-buses is related to their operations. And when we talk about the operations of electric buses, this is something quite different from the operations of the conventional diesel bus fleets that we've been operating over the past decades. And when it comes to electric buses, there is a clear gap or lack of expertise to operate and maintain these new technologies. And if they are being operated in the wrong way, then definitely we cannot exploit their environmental benefits, as I've been mentioning over the past couple of minutes. So that being said, hopefully the goal of this tool is to help fleet operators, electric bus fleet operators, addressing these challenges facing electric bus technology in mainly for city applications or for urban areas. Now, this slide provides a high-level illustration of the TUMI EBus tool. So in general, just like any other tool, the tool needs a set of inputs, and these are mainly fleet-specific data and inputs. And then the tool will execute some sort of coding and models and will provide some outputs. So inside the TUMI EBus tool, we have three separate modules or parts that actually interact among each other. The first part is about assessing the fleet energy needs. And this is the very first step. We need to understand what is the energy consumption of these new electric buses. We need to understand how much electricity they are going to require in order to operate according to schedule, and many other key performance indicators that we need to assess based on these energy needs. And definitely this step is the very first step, which will feed in directly into the next step or the next part of the tool related to simulating the fleet day-to-day operation under a certain set of design choices. The importance of this part is to understand how electric buses will actually operate under real-world conditions, taking into account their daily schedules. Because at the end of the day, the last thing we need is for these electric buses not to be able of respecting their schedules or not to be capable of completing their designated or assigned number of trips during the day. And the final step is to estimate or calculate the total cost of ownership of this transition from diesel to electric buses for several design choices. And I will be now digging into the details of every single module as we go on in this presentation. The main output now of this tool is to recommend the most cost-effective design choices to transition the current diesel bus fleets into electric bus fleets. And when I talk about design choices, again, I'm referring to the battery sizes and the charging infrastructure. So what type of chargers do we need, the charger's location, charger's number, and also the charger's power. So this is a high-level illustration of the model. Now let me dig deeper into each one of these three main modules to better understand what we are actually dealing with. So the first part about assessing the fleet energy needs. The idea here is that we would definitely need to estimate the energy consumption of these electric buses, and we would also like to minimize the number and the number of tests, the number of actual tests and experiments that we need to do, and also the time needed to conduct these tests, which is quite expensive and time consuming. So that's why we develop these physical energy models for electric buses, trying to be as comprehensive as possible. So this is a snapshot of the tool that we use to develop the models and estimate the energy consumption of the buses. We model the buses' longitudinal dynamics, and also we focus on the main energy components on board, like batteries, electric motors, transmission systems, the battery thermal management system, the bus cabin and the bus passengers compartment, heating and cooling needs, which is quite an energy intensive process, as you will see later in this presentation. So we try to be as comprehensive as possible in order to reflect on the real world energy needs of electric buses that are actually operating in some cities or in some location, in a specific location. And this energy assessment is carried out taking into account the mission profile of the buses, like the velocity profile as function of time, the road grade, also the weather conditions, which would vary from one city to the other, and also the level of passengers occupancy inside the bus. As you can see in this slide, I'm showing option 1 and option 2. So we actually do have 2 options to estimate the energy needs. Option 1 is definitely the more comprehensive one, which is based on this detailed modeling and takes into account this set of data. But we also understand that fleets might not have access to such data for some reason. So that's why we have another option, which is a simplified energy analysis that would take into account some average data like average speed, average occupancy, average weather conditions, which would be something very simplistic, but nonetheless, it would be representative of the energy needs of the buses. So both options are available, and depending on data availability, the user can go with either options. So that's it regarding this part of the tool. The second part now is about simulating the fleet day-to-day operation. So the whole idea here is to numerically mimic or model the EBus fleet operation, taking into account different set of design choices. Again, just to remind you, a design choice here refers to a combination of battery size and charging infrastructure. So how would the EBus fleet operate under these design choices? And in this basic illustration here, I'm just giving you an idea of what type of factors we actually take into account when modeling the fleet operation. So we take into account definitely the bus fleet, the operating conditions like driving conditions, passengers load, weather conditions, the location of the stop stations, the depots and the terminal stations, the geographic location, so the XY or the GPS coordinates of these locations. And most importantly, the fleet or the line schedule, which will be an integral component in order to numerically model the operations of the fleet. So this analysis, as I mentioned, takes into account fleet's schedule, origin destination data, and potential charging stations, and also grid limitations. So this is quite interesting because we have realized that in some urban areas, electric buses have already been operating for some time, but they face some problems when it comes to charging simply because there are some grid constraints in that specific geographic area. So this is something we have to look into, and that's what we're doing in this module. So the whole idea now is to monitor the bus's state of charge during the day, during operation, and the station's port demand. And we need to do that because we need to check if these design choices that we have decided to go with are actually capable of meeting the bus energy needs during the day and capable of respecting the bus's schedule, which is, we assume, to be fixed as a fixed input into this model. And as I mentioned, a design choice is actually only includes battery sizing, charger's location, number, and power. So that's about this second module. What we will get from this module now is, well, what design choices are going to be technically feasible so that electric buses will actually stick to their schedules. There will be no schedule disruption or any service interruption during operation, taking into account the bus energy needs and all these mentioned factors affecting the operations of electric buses. So that's about it regarding this module. Moving now into the last module of the tool, which is about the economics now of electric buses. So after defining or identifying the feasible design choices, so which design choices will be technically feasible to use for this specific fleet, we go on and start talking about the economics or the economic viability of these design choices. And to do that, we calculate the total cost of ownership, which we abbreviate as TCO in this slide, in this presentation, in order to comment on their economic viability or cost effectiveness. And in the TCO analysis, we try to be as comprehensive as possible. So we take into account the investment costs, the energy and fuel costs, so electricity cost or charging costs in this case, maintenance cost, infrastructure cost, if that's relevant, battery replacement costs during, let's say, the service life of the bus, and taxes if there are any. Just to have, let's say, couple of notes here. When it comes to investment cost, we understand that for the fleet operator is not always the fleet owner. So in some cases, the fleet operator does not actually incur any investment cost, but it's rather some sort of a leasing cost, like a monthly or a yearly cost, depending on the type of contract they negotiate with local authorities or with the fleet actual owners. So there's this flexibility to consider both options. Also, when it comes to infrastructure, we can model a couple of options here. So one option is if the fleet operator owns the chargers or owns the charging station. So that's one option. Or if the fleet operator is only using publicly accessible charging stations. And so we have different models or different business model for the infrastructure cost, which we also take into account. So after assessing the TCO of all the feasible design choices, we then go on and recommend the most cost-effective ones, because it only makes sense to go with the most cost-effective design choice to minimize cost or maximize profits in this case. One additional, I would say, piece of analysis that it's also interesting to have is to compare the TCO of this transition, or the TCO of electric buses, to the current diesel bus fleets. And this will also give a rough idea about the cost effectiveness of this transition from diesel to electric buses. So that's about the final module of this tool. Now I will be just summarizing the whole thing. So this tool actually is trying to help fleet operators overcoming all these challenges facing the deployment of electric buses by first assessing the energy consumption of these buses. And for that, we need to take into account the bus operating conditions, like the drive cycles, weather data, passengers occupancy as well, in addition to the bus technical specifications. From this module, from this part, we get the bus energy consumption or the bus energy needs. The second part of the tool is about simulating the fleet daily operation. And again, for this part, there are some specific set of data, most importantly, the schedules of the fleet, of the bus fleet. And from this module, we get what are the different feasible design choices in terms of what type of batteries do we need and what type of charging infrastructure we would need in order to ensure we have a smooth operation without any service interruption or any schedule disruption during operation. And the final module is about estimating the total cost of ownership of the different technically feasible design choices. And for that, we definitely rely on lots of cost data, which we already have. And also we rely on some location-specific cost data, like local diesel fuel costs or prices and local electricity costs and tariffs, in addition to many other inputs that are well documented in the tool. And finally, the main outcome of the tool is to recommend the most cost-effective design choices, definitely cost-effective and technically feasible design choices that would help fleet operators transitioning from the current diesel fleets into electric bus fleets. So that's about the first part of this presentation, which is a high-level presentation of the TUMI EBus tool. Now for the rest of the presentation, so for the next roughly 15 to 20 minutes, I will just present a use case for an electric bus line operating in a Latin American city, which is to remain confidential at this stage. Just to give you an idea, like what type of inputs you might need and also what type of outputs you should expect from this tool. So let me start with this first slide, which is about the user inputs, definitely, like what type of inputs do we need from the user in order to execute the tool and get the results. So the first type of inputs are related to the energy assessment of the fleet. And as I mentioned earlier in this presentation, we do have two options here. The first one is a detailed energy analysis, which in this case would be definitely an accurate assessment of the energy needs. And for that, we would need the driving or the velocity profile of the buses, like a representative velocity profile of the buses as function of time, as you can see in this figure, like the road grade profile also as function of time, some data on the passengers' occupancy during the day, and also on weather conditions data, which is something I would say quite easy to obtain. But mainly it's all about these driving conditions data, the cycle velocity, and also the road grade. This option will provide a very detailed energy assessment. And also just to mention that all these energy assessment models that we've been developing in-house have been validated against real-world data collected from a couple of pilot projects we've been actually having in a couple of Latin American cities as well. So this is the first option for the energy assessment. The second option, which is a more simplified energy analysis approach, it only takes into account a handful of parameters and inputs, as you can see in this table. Like, what is the average trip speed? What is the average acceleration, if that's available? What is the trip distance, duration, average number of passengers per trip? So it's all average data that can be easily obtained. So in the case of lack of data availability for the fleet operator, they can just input basic and simplistic average data, and we can conduct this simplified energy analysis and assess the fleet energy needs. Just to mention that this second option doesn't take into account the road grade, which could be significant if there are some, I would say, considerable elevation changes in a certain geographic area. And definitely, since this is a simplified approach, it is less accurate than the detailed one, but nonetheless, it is still an acceptable energy assessment of the fleet energy needs. So yeah, this is, I would say, the first set of inputs that the fleet operator or the user would need to provide. Also, another set of inputs related to the operations of the fleet. And just to mention that the user will be filling all these relevant inputs in a very simple Excel spreadsheet. So as you can see, we have like the Excel spreadsheet, and as you can see in the bottom of the slide, like we have a couple of Excel sheets defining some specific inputs, like general inputs, defining the lines or the routes or the route distances, inputs about the schedules or the power constraints, if there are any. So it's really a user-friendly environment where the user will be filling some inputs, and then the tool, the TUMI EBus tool, will automatically read all these inputs and will conduct or execute the code and the analysis, and then provide the outputs in a separate Excel file. So the user do not need to do anything manual in this case. So data about the operations, like we also would like to have data, like general data about the fleet. For example, the number of buses operating in the fleet. How many lines do we have in this case? For example, some fleet operators operate the same bus across 2 different lines during the day. So that's an option, which is, would say it's quite common. How many depots, how many big terminal stations do we have for this specific fleet? The number of main stop stations, that's quite an interesting one. So we understand that it wouldn't be reasonable to ask the user to input every single stop station, or like the coordinates, or the to define every single stop station along the line. That's definitely not efficient. So what we propose is to define main stop stations, and a main stop station is a stop station that could potentially serve as a charging station. Like usually, if there's a very large stop station connected to a certain metro station, or like a railway station, or a commercial center, so that could be a potential charging station. So if that's something available, that can also be defined in this in the tool. And as you can see, we also have like some basic inputs, like the fleet operation starting time during the day, and like the minimum dwell time in minutes, depending on the use case. I would say the most important input for the operational aspect of the buses, of the electric bus fleet in this case, is their schedules. So based on whatever inputs the user will have in the based on the previous slide, the tool will generate this automatic spreadsheet where the user would need to input the arrival time and departure time of every bus, or like the bus fleet, from some dedicated stop stations, mainly the depots or the terminal stations. And that needs to be done. That should be done for all the buses in the fleets. This I would say this is an easy task for fleet operators, simply because most of these schedules are digitized, and that would be hopefully an easy copy paste input into this tool. So once we define these the schedules of these buses, this would be, I would say, the most important input for the operations of the EBus fleet. The final set of inputs is about the economics of the EBus fleet. So there are lots of data needed to understand or calculate the TCO, the total cost of ownership of electric buses in general. Luckily, most of this data is already built into the tool, like data about the financial assumptions, about the service type of the buses, about like lithium-ion battery cost, and many other sets of data. Most of these are actually built into the tool, but definitely we would still need some location-specific data, like if there are any local taxes, but more importantly, what are the local diesel fuel prices? What are the local electricity or charging costs in a certain geographic area or in a certain city? So definitely, if the user has more representative data of their fleet, that would be more representative, trivially in this case. But the tool is already built in with lots of default input data. I just would like to highlight one important aspect of this economic assessment, which is the charging cost. So the charging cost will be the main component of the total cost of ownership, how much it's going to cost to charge these electric buses. And here also we have a couple of options to do that. So we have one option, which is based on detailed charging cost modeling, taking into account the dynamic time of use tariffs during the day. So if electricity prices change during the day, we can actually catch that. If there are any demand charges, this is more of an issue in the US rather than Latin America or other regions in the world, but we can handle such changes and such modalities. In addition to many other inputs, as you can see in the slide. We also take into account the possibility of different business model for the charging stations, as I have mentioned earlier. So if the charging station is owned by the fleet operator, we do provide data about the charger's cost, the hardware cost, and the installation cost of the charger, definitely depending on their power demand, on their power rating, in addition to data about their operational expenses. Just to say that there is this option of having a very detailed charging cost modeling. On the other hand, if the fleet operator is only accessing or only using publicly accessible charging stations, which charge a certain, I would say, dollars per kilowatt hour energy. So that's also an option. That's a more simplistic option, but it is there. So the user can just input this dollars per kilowatt hour charging cost, and it will be as good as the first one, the detailed charging cost modeling. So just to highlight that we have both options here, and also this could be interesting from the perspective of a charging station owner or operator in this case. So that's regarding the economics. Yes, so that's regarding the economics of electric buses. These are the set of inputs that we would need. And let's move to the more interesting part now, which is the expected results. So what type of results we should expect, and yeah, how to analyze or to read these results. As you can see in this slide, the first main output of this tool is the energy efficiency or the energy consumption of of these electric buses. So in this specific slide, I am showing the energy consumption of the average energy consumption of the bus fleet under different operating conditions, like between 25 degrees and 35 degrees C, and for different levels of passenger occupancy. You can see that the energy consumption is highly sensitive to weather condition and bus ridership. So it increases from 0.85 to 1.4 kilowatt hour per kilometer, which is a significant variation. We also provide a detailed, I would say, energy assessment or detailed energy consumption breakdown. For example, here we quantify the electric motor or the propulsion motor energy consumption, the air conditioning unit energy consumption, and also the other auxiliaries energy consumption. For example, in the case of if external temperature is really high, like 35 degrees, so it's a hot weather condition, the AC consumption is significant. As you can see, it has significantly increased relative to a average ambient or moderate ambient conditions of 25 degrees C. Same thing applies for the number of passengers. If we have a higher number of passengers, the total energy consumption of the bus would also increase. So just to mention that we do need this detailed energy assessment under a variety of operating conditions, because the energy consumption and the energy needs of the electric bus fleet will be highly sensitive to these operating conditions, which will reflect on their charging needs and also on their schedules as well. So that's about the first main output of the tool. Moving now into the second type of outputs that we should expect, and this is really about the technical feasibility of different design choices. In this slide, I am summarizing, I would say, like 5 or maybe 6 different design choices here. So a design choice is, for example, a combination of all these inputs. So battery size, charger's location, number of chargers, and also the charger's power. Let us go through this like just for a minute or two. So for the first option here, we have a battery size of 200 kilowatt hours. We have depot 1 only equipped with chargers, and this depot has 4 chargers only, and the charger's power is 100 kilowatt. So this is one design choice. And based on this feasibility assessment that we conduct, it turned out that this design choice is not feasible because the buses ran out of energy during operation. So the buses were not capable of completing their trip, or the buses were not capable of completing their assigned number of trips during the day. So that's definitely not a feasible design choice. For example, option 2 seems like a feasible design choice, which is, like we have for the same battery size, but we have more chargers here. Option 3 is not a feasible one, and so on and so forth. Option 5 is an interesting case to look at. So we have big battery, 400 kilowatt hour, which I guess would be enough to cover the whole the daily needs of the buses without the need for recharging. We have a very high number of chargers, but that was not feasible simply because we had grid power limitations. So in this example, there were some grid power limitations. We cannot exceed a certain number of kilowatts during charging. So that was a different type of limitation, resulting in a non-feasible design choice in this case. And as you can see, some of them are acceptable, the ones in green, and some of them are not, the ones in gray. Just to mention that the tool actually examines like hundreds, or actually I would say a couple of thousand design choices, and I'm just showing like 6 here. So we examine so many design choices, and then we try to filter which one are actually technically feasible in order to proceed into the next step, which is about the cost effectiveness of these different design choices. So as you can see here in the slide, I'm also showing only 4 different options. And we have these 4 options for regarding the feasible design choices. And we estimate the TCO of every single design choice. So design choice number 1 resulted in a certain TCO. Design choice number 2 had a slightly higher TCO, and so on and so forth. And at the end of the day, I mean, trivially, we would definitely recommend the most cost-effective design choice in this case for this specific use case, or for this specific EBus fleet. There is no one, I would say, right solution here. I mean, simply because there are we might have some trade-offs as well. For example, this solution here has the lowest TCO. Solution number 2, which is slightly equipped with slightly bigger batteries, like 300 kilowatt hours, it has a slightly higher TCO. But bigger batteries can provide more operations flexibility. So this is really up to the fleet operator or to the user to determine which one of these solutions will fit their needs the most. So what we do is we just recommend these as the most cost-effective solutions, like the best 5 or the best 10 solutions in terms of technology feasibility and cost effectiveness. And then the user can actually choose which one would fit their needs the most. One last point to mention in this slide is that we can compare the TCO of electric buses with their diesel counterparts. So in this case, we already had a diesel bus line operating, which we would need to replace with electric buses. And we estimated the TCO of the diesel bus fleet, which was about, as you can see in this example, $1.12 per kilometer. This will give an indication of how cost-effective the transition from diesel fleets into electric bus fleets. So as you can see in most cases here, operating and owning an electric bus fleet was much cheaper than operating and owning a diesel bus fleet for this specific use case I'm just demonstrating the tool about. So I guess that's it. I guess I still have one last slide. Let me see. Yeah, a final slide, and then we can move into the Q&A session. It's about another very important output, which is the charging stations power demand during the day. So the issue of charging infrastructure is really becoming the bottleneck for the wide deployment of for e-mobility, for electric mobility in general, for passenger vehicles, for trucks, and probably for buses. So it's very important to understand what would affect, how the large-scale deployment of electric buses would affect the power demand from the electricity grid, from local electricity grids. And that's why it's important to try to quantify the charging station power demand during the day, and why not in real time, as you can see in this figure. So we do have, as you can see, the fleet charging power during the day. We can already identify some peaks. For example, we have a peak at, I would say, 11 or maybe 10 a.m. We have another one at 3 to 4 p.m. here, exceeding 300 kilowatt. And then at night, we have like a fixed charging peak at 100 kilowatt. So this will help the charging station owners or operators, or even the urban planners who are actually working on implementing charging stations, just to understand what is the expected power demand to serve a fleet of electric buses in this case. And this will be very important, especially when we start examining different possibilities to reduce these peak power demands, which might have an impact on the cost, or might have as feasibility issues, as I have shown in a couple of slides earlier. So this is the final slide of my presentation. I hope you enjoyed it, and yeah, let's jump into the Q&A session.
Thank you so much, Hussein. I'll ask my colleague Mende to share our final slide, but while we're doing that, we do have a few questions lined up for Q&A. If there are any remaining questions, we again encourage you to drop them into the chat. I think we can start off with this question of how you are factoring in the battery replacement cost, and is it based on the number of kilometers used or the number of years used?
So yeah, in this tool, we are actually considering battery replacement as a function of the battery service years. So it's depending on the number of years, but not on the number of kilometers, because from our experience now with electric bus manufacturers, most of them are actually providing guarantees, battery warranties for like specific number of years, like maybe 5 to 7 years. This definitely depends on the contract negotiated between the fleet operator or owner and the bus manufacturer. But we can actually consider both approaches in battery replacement. At this point, it's only about the number of years, but definitely the number of kilometers is just an easy ad hoc into the tool.
Great, thank you. We can move on to the next question about the grid constraints you mentioned. Someone is asking for more details and mentions that in many cases, these models may suggest depot overnight charging or en route fast charging, but the decision will often come down to required grid upgrades. And is it possible to add these considerations to the grid constraints?
So yeah, maybe a couple of comments about the grid constraints. So what we model here is, let's say if we have a potential charging location in a depot or in a terminal station or in a commercial center. So we identify this as a potential charging location, and we examine the possibility of equipping this location with a certain number of chargers that have a certain power demand. And then we try to get data about grid limitations for that specific location. And then we should respect this maximum grid limitation. So this is a no-go in the tool. So if the this charging station power demand exceeds the grid limitation, then we just decide that this is not technically feasible. But as mentioned in the question, it is possible to examine the possibility of having some grid upgrades, which would increase the maximum power capacity of that charging station. But this would be a very expensive, I would say, process. And we don't really believe this would be a cost incurred by the fleet operator. And this whole tool, this whole analysis actually being conducted from the perspective of the bus fleet operator. So that's why we decided that was not very relevant for this tool. But the question is very valid. Yeah.
Thank you. Another question on what the tool accounts or does not account. Does it account delay times? And I'm assuming that's asking about charging delays or any route delays by the driver.
Yeah, that's an excellent question, actually. Definitely charging delays are at the core of this tool. So basically, we have a certain number of chargers and we have a certain number of buses. And for some reasons, or let's say for some under certain conditions, some buses might have to queue to recharge, or some buses might not be capable of fully recharging their energy needs because they have a trip that they need to catch up with. So the idea is that these delays are actually factored into this this tool. And as I mentioned earlier, also, like when we realize that there are some unacceptable delays exceeding a certain, let's say, number of minutes per day, or let's say, depending on what is acceptable and what is not acceptable in a certain region, when we see that's the case, then we decide that this is a non-feasible solution. So we either need to increase the number of chargers or increase the charging power, which will result in a higher cost. So yes, short answer is delays are factored in into this tool.
Thank you. There was a follow-up question about congestion and if the approach considers congestion as a factor. And I assume similarly to other types of delays, congestion and traffic would be one of those considerations.
Yeah. So in this case, not really. Congestion is not taken into account because the tool actually is based on the main input is the scheduling of the buses, which is a fixed input. It's not really something dynamic. So that's not taken into account. That's definitely something we would need to think about during the next, I would say, update of the tool. Yeah.
Great. I know you mentioned this during the presentation on the sort of elevation of the city and if it was relatively flat or relatively slopey. And someone is wondering if you have any data from this tool for a city located in the Highlands that you can share for research purposes.
I don't exactly know. My colleagues, mainly Oscar and Carlos, they are the ones leading on the data collection, and I can double check with them and get back to whoever asked this question. Yeah.
Sure, we'll make a note of that. And then on slide 12, which I believe Mende should be able to go back to. If not, we can just switch the screen share again. can you comment on the accuracy of both approaches for the energy assessment of EBuses?
Okay. Yeah, I don't think that was the meant slide. Can you move to the next one maybe, or probably this one, I guess. Yeah. So yeah, on the energy, yeah, exactly, the accuracy of both approaches. So yeah, for the first option, which is the comprehensive energy assessment option, we actually fine-tune and validate these models relative to some real-world data that we've been collecting in a couple of pilot projects. And so this is quite accurate, and based on our own validation, this is really within a ±2% error relative to the real-world data. For the second option, this is the more simplified option, which has some limitations, definitely. We definitely have higher errors here, higher margin of errors, ranging between 7 to roughly, I would say, 10% in this case.
Thank you. And while we're in the presentation, we did have a technical question on the tool. And Dave, you can jump to slide 24. Someone is wondering about what type of data formats the tool can handle for imports, specifically on timetables.
Yeah, any CSV data would be can be read easily. Regarding other types of data, I don't exactly know if we can. It is not yet capable of handling other types of data, but I think that's an easy fix. But that will be like on a case-by-case basis.
Great, thank you. Let's see, for next question, again, quite technical. Does the tool have any machine, back to congestion actually, does the tool have any machine learning to learn the effect of the congestion on the fleet timetable?
No, it does not, no.
Another next version upgrade. One question just came in the chat. Is the cost per kilometer of the diesel bus able to be modeled with the case evaluated? So I guess asking about a comparison.
Sorry, come again. Is the cost of the diesel bus, so can we model
cost per kilometer
of the diesel buses? Yeah,
yes.
So we have already, I guess, in some of the slides, I have shown that we can do that. And I guess if you go to slide 28, yeah, just this one, exactly. So we have already modeled the, so maybe I didn't make this clear. This is the modeled diesel bus fleet TCO in dollars per kilometer, which is something we've also validated against the currently operating diesel bus fleets in a certain Latin American city. So yes, we have that possibility, or simply the user, I mean, the fleet operators who already know the total cost of operation of their own diesel bus fleets, they can just compare the results to whatever they have. Yeah.
Great, thank you. I do encourage anyone that may have any remaining questions to put them in the chat. If not, I can ask a final question on sort of the scalability or future of this tool. Sort of what are your goals for applying it to other cities or other regions? And can it be applied in regions outside of Latin America?
Yeah, definitely. So this is really, I would say, location agnostic. So it's really, it would work in any location, and also it would work for several different types of business models when it comes to owning and operating electric buses. What matters is the representativeness of the inputs. So it's really the user's homework to define what is a representative set of inputs for their use case, so they can actually make the most out of this tool. So yeah, the short answer is this would work in any region in Latin America, and the US, the EU, India, and pretty much anywhere. When it comes to the future updates, or what's the next step for this tool, we are currently trying to have like some sort of pilot projects with some fleet operators in order to like collect more data, keep improving the tool, and try to understand if there are any like hidden challenges that we didn't actually spot in this tool, so that we can actually integrate these new challenges or these new functionalities, assuming that fleet operators are interested in. So basically, it's going to be about doing some live case studies in some probably Latin American cities, publish some documentation about the tool, and also we're going to examine the possibility of making the tool either a publicly accessible tool, or we're going to just reach out to fleet operators for them to use the tool and also get their feedback, and try to integrate their feedback into the tool as well.
Great, thank you. That's great to hear, and definitely look forward to hearing if it does become publicly accessible. I think for our audience here, who is mostly based in Latin America or South America, if there is interest or further question in the tool and potentially applying it to your own city or learning more about the coalition, we will be sharing some contact information as well as a recording of the presentation after the event. So again, thank you so much, Hussein. Thank you to the ICCT as a TUMI coalition partner. If there are no more questions, I think we can wrap up. And thank you all for joining and for participating.
Thank you, Lidia. Thanks all.